couple more examples of our integral tests. So we have this series n equals 0 to infinity, 4 over the cube root of 2n plus 3. And so we're just going to use our regular method where we're going to take the limit as c approaches infinity, integral from 1 to c of 4 over the cube root of 2n plus 3, right? Now, once again, we're going to need a u substitution to be able to evaluate this. And I'm going to change the n's to x's. So this is going to be a 2x plus 3 and then dx. And we're going to go ahead and use a u substitution for what's under the cube root. So u is going to be equal to 2x plus 3, right? Our du is going to be 2dx, all right? And even though I could factor the 4 into 2 times 2, I'm just going to divide by 2. So du over 2 equals dx, all right? And so our limit as c approaches infinity, integral now from a to b, okay? So not from 1 to c. And we're going to have the 4. We're going to have the cube root of u, and then we're going to have du over 2, okay, instead of dx. Right? Now, if we want to simplify this and also set it up for integration, we can now rewrite this as the limit as c approaches infinity of the integral from a to b, 4 and 2 simplify to 2, and then we're going to have u to the minus 1/3 du. Right? Now we can just go ahead and use our regular integration rules. So we get the limit as c approaches infinity of 2u to the 2/3 divided by 2/3 from a to b. I'm going to back substitute for u, which we said was 2x plus 3. So now we have the limit as c approaches infinity. This is going to turn into 6 over 2, which is going to be 3. And then we said we had 2x plus 3 for our u to the 2/3 power from 1 to c. And finally, now I can substitute c back in. All right, so this is now going to be the limit as c approaches infinity of 3, 2 times c plus 3 to the 2/3. And then we could substitute 1 back in, 3, 2 times 1 plus 3 to the 2/3. And when we substitute infinity back in, all right, we know that infinity raised to the 2/3 power is going to keep getting bigger and bigger and bigger and bigger, okay? The only time that it's going to go away is if c is in the denominator for us, or we have a negative exponent. So we just really end up with infinity minus 3 times 5 to the 2/3 power, which is equal to infinity, which is clearly not a real number. And so what we can say is that this is going to be a divergent series because the integral also diverges, okay? So it diverges. One last example, and this is a pretty good one, a little bit sneaky, but we have n over e to the n, all right? And for this one, what we're going to do, let's just go ahead, replace the n's with x's, set it up as a limit. Okay, so we're going to have the limit as c approaches infinity, as usual, 1 to c. And I'm going to rewrite this as x e to the minus x dx. Okay. And again, we could just rewrite this series if we really wanted to, okay, as series n equals 0 to infinity of n e to the minus n by moving that n up, okay? And so what I did was I just substituted back in for n and just made that x, okay? Now, to be able to evaluate this, we can't use a u substitution. In fact, we can't use any substitution, so we're going to have to use our parts formula, okay? And just in case you guys forgot the parts formula, we're going to say that the integral of v du is equal to uv minus the integral of the integral of u dv is going to be equal to uv integral of v du. Okay, so that's a u. So I'm trying to separate the u's out because they're tougher to see on the screen. All right, and you probably remember that what we have to do is we have to define u and v and dv, excuse me. And u, we like to make that something that when we take its derivative, it's going to reduce in power most of the time. Okay, so let's let u be equal to x, and let's let dv be equal to e to the minus x dx. Now du is going to become dx, and then dv, if we take the antiderivative of e to the x, technically it's going to be e to the minus x over minus 1. Okay, because remember, we divide by what the coefficient is. Well, we could just rewrite that as negative e to the minus x. Okay, so these are little tricks that we should be picking up throughout the course as we've seen them multiple times. All right, so now we're going to substitute into our formula. So now we have the limit as c approaches infinity. We have uv, which is going to be the opposite of x e to the minus x from 1 to c, minus the integral of v du. So that's going to be negative e to the minus x dx from 1 to c. Now I'm going to hold off on evaluating all of the taking the limits and applying all that stuff until we're done with all the integration, okay? Just to make it a little bit easier for us. The good news is evaluating this animal is pretty easy at this point, okay? So now we have the limit as c approaches infinity. We still have our negative x e to the minus x, so that's our uv from the previous. And then this, we have a positive, but when we take the antiderivative of e to the minus x, that's a minus e to the minus x, okay? And remember, this is going from 1 to c, and now we can substitute c back in, okay? So this is going to now be the limit as c approaches infinity of minus c e to the minus c minus e to the minus c. And then I'm just going to throw the 1 back in. So minus a negative 1 e to the minus 1 minus e to the minus 1. All right, now this is easy for us to evaluate, right? This stuff's pretty easy. We just end up with minus a minus 1. So all of this is going to turn positive. And really, we just get 1 over e plus 1 over e. So this becomes 1 over e plus 1 over e. Or this part is just 2 over e. So let's hold on to that. This part right here is a little bit sneakier, okay? Because now we have the limit as c approaches infinity of the opposite of c over e to the c minus 1 over e to the c, right? Now think about this. If we applied the limit to this second part, well, that would just become 0 because we would have 1 over infinity. So this just goes to 0. But what about this animal? Well, that actually goes to infinity over infinity, or negative infinity over infinity because of the negative sign in front. And so we could just use L'Hopital's rule on this guy right here by taking the derivative with respect to c of the numerator and denominator. And so that becomes the limit as c approaches infinity of the opposite of 1 over e to the c. And again, that was 0, so it doesn't really matter. And we know that this is going to go to 0 as well. So really what we end up with, this whole thing goes away. We have 0 plus 2 over e, and we have 2 over e, which is indeed a real number. And so what that means is that we have a convergent series, okay? So remember up here that the series converges. Now, again, note that it does not converge to 2 over e, okay? That is not the sum of the series, okay? So just to make sure that we're really clear on this, okay? That this is not the sum of the series, but it does converge to a value that's in the neighborhood of it, okay? So the series n equals 0 to infinity of n over e to the n does not converge or does not add up to that 2 over e, okay? And similarly up here, it doesn't add up to infinity because it can't, okay? But for the other ones that we did, I think we had one that was convergent, one that was divergent, or two, I'm sorry, two convergent, two divergent. For those that are convergent, it doesn't add up to that value, okay? All right, so our 3 tests that we looked at the test for divergence, we looked at the p-series test, and then we took a look at the integral test. Again, on that sheet of paper that I suggested before, you may wish to go through and start writing down the different tests, okay? Because we do have several more tests that we have to go through before we can actually get to applications of our different types of series. So in our next section, which we're going to take a look at, we're going to start taking a look at comparison tests. So we have something called the general comparison test, and then we have limit comparison tests. So again, a lot of tests. None of them are overly difficult algebraically or calculus-wise, but there are a lot of them. Okay, so it's making sure that you have all of the different rules for the tests in one place.